So we're going to talk about making humans and code GPU capable today. So I'm Emily. I'm from Atlanta, which is the best city in the world. Um, I'm not a data scientist. I've spent my whole tech career, working alongside data scientists without actually being one of them. So that's kind of where I see the empathy of like watching data scientists do their work and trying to help empower that. Um, so our goal here, where the highlighting is really off, our goal here is to help data scientists do higher quality work faster. That to me is the whole goal of ML Ops, is to empower our data scientists. And in this realm of ML Ops, this is a hyper technical field that is all about people. So I'm really trying to drive this home here. Like, this is hyper technical, but it's all in service of our data scientists. This is an inherent push pull already in design trade offs, that we have this hyper technicality that also has to be used by people. And this just fits along with a lot of the other design trade offs that we talk about in our space all the time. So Jules had a great little diagram touching on some of these similar design trade offs, like, is it friendly for developers or is it fast for computers? That tends to be a trade off. Our Spark jobs would be a lot faster if we were all working in C and writing inline assembly and, messing with P threads and all that kind of stuff. So raise your hand if you're doing that. Right. We fall along these different sides of the spectrum for different reasons. So with all this kind of context of design trade-offs, let's talk about our typical machine learning stats. I'm presenting this in kind of a general way, but you'll probably recognize this. We're all using Python. It's the second best language for any task. You've got all your Python machine learning libraries. It's probably containerized. You're probably running on cloud infrastructure. You're probably using Kubernetes either directly, as in you're spinning up your own cluster, or indirectly, as in you're using a branded product that is almost certainly Kubernetes under the hood. So the benefits of this, we get great scalability and we get good reproducibility if we do this right. So we really need that kind of ephemeral infrastructure and big scalability in our world. So if you're running a web service like, Mailchimp.com, maybe you're running an all-in-one small business marketing platform, your infrastructure is a lot more steady state in terms of its traffic. So it's about here and it'll drift up to here and down to there throughout the day, but it kind of stays in that range. For us, with batch jobs and with training jobs, we're either all on or we're all off. There's not a whole lot in between. Serving is a little different, but you get my picture. So we really like this cloud world, being able to spin up and spin down and have this ephemerality. But there's a problem that comes in when we have these magical ephemeral containers that are running somewhere, and they need to talk to very real GPUs that are not ephemeral and not virtualized and not made up. They are real, actual hardware. So let's talk about these GPUs. They're real buzzy, Bitcoin, rendering your video games. You can't really buy them. Super hype train, blockchain, investors love that. And legitimately, they can be really, really awesome. So this is a graph that I'm particularly proud of for two reasons, showing what happened to one of our services when we flipped on the GPUs. The first thing I'm proud of is that there was zero downtime when we did this, which rocks. But also, look what it did to our response times for that service. That's pretty cool. It cut it in a third or even more. So GPUs can be really, really helpful for us. To kind of put this in concrete terms, GPUs are optional hardware peripherals that require really special, really finicky drivers and rely on system buses for I/O. So really, if you kind of generalize this, GPUs are printers. Because what is a printer but an optional hardware peripheral that requires just super finicky drivers that are really annoying. So GPUs are just printers that are really good at linear algebra. So hopefully I'm popping the hype bubble a little bit. Um, if we think about, uh, let's talk about what the call stack would look like if we were running one of our online services on an actual physical server. So we could walk on down to the data center, see the server, poke it, see the actual GPU inside. This is kind of what that call stack would look like. So the top three layers are kind of familiar to our data scientist crowd. That's kind of their core area. You've got your service framework that's underlying your custom Python application that's depending on some sort of open source machine learning library. Underneath that, and we'll dig into these next two layers a lot more in just a minute, you've got your Cuda libs, your device drivers. So that's kind of your middle layer before you hit your operating system. And that operating system is running on like a physical server that you can poke and that has a physical GPU in it. So still a lot of layers here, but pretty linear in terms of what we're going to do. So, and you can still mentally substitute GPU for printer, if that helps. In the ephemeral world, this gets a lot more complex. So we still have our same top three layers in green that we've containerized, that we've stuck inside a pod, except that pods are actually lifecycle objects, but you know what I mean. And that's running on Kubernetes, which is running on a whole bunch of virtual servers that are in turn running on like cloud stuff, hypervisors, all that jazz, where eventually you get down to a physical server that eventually has a physical GPU. And I kind of cut out all the CUDA stuff because it didn't fit on the slide and because that's kind of the rub of how do we get that middle layer in there. So these are kind of the key pieces in that middle layer to talk to your GPU. And I do want to caveat really hard here that I am specifically talking about Nvidia GPUs because realistically, they have a monopoly. Heaven help you if you were trying to use ARM or all that ROCm stuff. It's pretty much Nvidia's world right now. So you have your Nvidia GPU. The next two things you need are your drivers. So you've got a kernel space driver and a user space driver. So nvidia.ko and libcuda.so is the one you've probably seen. Nvidia calls this their user space driver. Most other folks call this the low-level API. On top of that, you've got your CUDA toolkit. So the key piece here is libcuda.rt, which is your higher level API. And on top of that is stuff that you might start to recognize, like kublost, kurand, kudnn, all that kind of stuff. So we've got to get all those pieces kind of marshaled into our containerized system here in order to make this communication work. So first, we're going to get our GPUs and we're going to get our device drivers from your Kubernetes provider. So we happen to be on GCP. There's some GKE isms happening in this talk, but this is probably going to transcend cloud providers. In GKE, you can get your GPUs just kind of through your cluster configuration. You can set them up. You can get scaling GPU pools. That's cool. The key part here is this daemon set. That's the second step. So you've got your cluster that's got some GPUs on the back end. What this daemon set does is it runs around to every single node in the cluster and runs something that's specific to modifying that node. So this is really perfect in this case because this daemon set is running around to install all those device drivers on the actual node, talking to the node's operating system and kind of underneath that Kubernetes layer. Your cloud provider and your Kubernetes service is going to have some sort of pinned Cuda version that it can support. For GKE, when I took the screenshot, it was 11.0. That might have changed. I haven't checked. So that is still, it's kind of relatively straightforward about how we get those GPUs and how we get those device drivers. But that next layer gets a lot more complex. So how are we going to get libcuda RT and kind of that CUDA toolkit stuff that we need to support our machine learning libraries? Sometimes these will ship with your Python libraries. So this is very dependent not only on the library you're using and how they choose to package it, but also what Python package manager you're using. Because did you know that pip wheels and conda wheels are not guaranteed to be one-to-one? And some of the key differences are in where they package these binaries and that kind of thing. So lots and lots of variability here. When these shared objects get shipped with your Python wheel, they're still dynamically linked. They're just packaged in there such that those shared objects are going to be the first thing that your dynamic linking path hits. So usually this doesn't include the user level driver libcuda.so. This is usually everything above it. So you might luck out. It might just come with the wheel and you'll be set. Or another option, you might get some of this from your device driver set and your kind of what that daemon set that you installed on your cluster is doing. So in the case of GKE, it will forward a whole bunch of Nvidia stuff to things like user local lib Nvidia or something like that. So you can just point your dynamic library path to that folder and voila, you've got access to stuff like libcuda. But this usually doesn't have the CUDA toolkit stuff. So if those two options fail you, you're going to have to DIY it. You're going to have to install these manually in your container at build time or build off a base container that's already got these installed and already has your dynamic linking paths kind of set up. More likely, you're going to have to do a combo of all three of these, just depending on what library you're using, what Python package manager you're using, what version of your library you're using. It's wild. So once you've gotten through kind of where you're going to get these pieces, it's really important to think about matching your Cuda versions all the way up and down the stack. So what does your GKE cluster support? What does your container support in the stuff that it's got pre-installed? What was your machine learning library built against, and what does it support? So you want to have, if you're standardizing on 10.2, you want to have 10.2 in your cluster, 10.2 in your container. Your library is built against 10.2. You want to match that all the way up and down the stack. Asterisk. Usually, sometimes, depending. This stuff is so fun. Your mileage may vary depending on your library. So this is kind of a tale of two deep learning libraries here. If you dig around in the PyTorch source code, eventually you'll come to one of these header files that's got one of these great 300 line comments at the beginning of it that's like, okay, you found this header file and it's kind of nuts and you're probably wondering what this is and okay, here's the deal with that. And I love when you find that stuff deep in the stack. What it boils down to is that the PyTorch project made a design decision to support both CUDA 10.2 and 11.0 at the same time. They are doing that by kind of wrapping all the CUDA toolkit stuff in their own PyTorch distribution of that. So when you get the PyTorch wheel, it is shipping with some binaries, but it's not kublos and kurand and all that. It is libkutorch because it's their specific version that's wrapping both of those CUDA versions at the same time, and then doing a whole bunch of really careful header guarding and if-defing to support both of those at the same time. TensorFlow does not. TensorFlow is kind of a diva. Each version of TensorFlow relies on extremely specific versions of all of these underlying libraries. So extremely specific major versions and minor versions and sometimes patch versions, and sometimes they don't even match. So you need 10.2 of this, but you need 10.4 of that. So it has a different experience for us, the end users. And just, I guess we're all we're going to wrap around to the design trade-off discussion, but a moment of design trade-offs here. I know which one of these design trade-offs I prefer as an end user, but these library developers are in a really tough situation thinking about how to manage all this stuff. So these are two equally valid options. And really, although as an end user, I really prefer the PyTorch method because it makes life easy for me, those PyTorch developers sign themselves up for a world of tech debt. So, like, pity them. So TensorFlow might have the end user experience of being a house of cards, but there's a reason it's like that. Something else I didn't cover there. That's right. So as we're finishing up this discussion on Cuda versions, the Cuda stack itself has extremely complex backward and forward compatibility rules. So Cuda's always had some form of backward compatibility along the stack. And then starting in version 10.2, they now have forward compatibility as well. But it's not quite all up and down the stack. It's like this little piece is forward compatible with that or backward compatible with this. So you can grab these slides later, follow that link, see all the complexities there. But that's just another bit of like, you want to match your CUDA versions sometimes. So a really cool trick for helping you get through this hot mess, strace and ltrace. So ltrace, you can just kind of do like ltrace Python invoke my awesome application or whatever, and it'll show you every single call it's making to a dynamic or static linked library. strace is kind of a similar deal. It's not doing library calls, but it's catching all of your syscalls. And importantly, in this, which I'm very excited about, and which I'm sure you can't read, it is going here. I'm using strace to run my application, and then I'm grepping for a whole bunch of CUDA output. And what's catching for me is every time these libraries go to get opened. So in this version of that slide, which is still not great, but maybe it's a little better, it's going through and it's saying, okay, I got libtorch. Again, that's that PyTorch thing. It's not shipping cuDNN or whatever. It's shipping its own PyTorchy stuff. I've got libtorch. That's fine. I've got libtorch CUDA _cu. That's fine. I got libcuda RT. I'm looking for libcuda.so, and I didn't get it. So I'm going to look in a different directory, and I didn't get it. And I'm going to look in a different directory, and I didn't get it. And that whole long output slide is just searching for libcuda.so and not finding it, which for me lets me know, aha, you can't find libcuda.so. And the library level error messages probably didn't tell me that because this ecosystem is great. So that's kind of the technical piece of how do we enable code to be GPU capable. Now, the second piece of this is how do we enable this for people? Because what I don't want to do is go to all of our data scientists and be like, cool, okay, let me give you a presentation about GPUs and libcuda and let you just have this knowledge and go figure it out. That's not the best thing. Because there's typically this gap between a typical data scientist system needs and a typical data scientist's system knowledge and experience. Or if you have some of those unicorn data scientists like we do at Mailchimp who do have that lower level stack experience, you can substitute in here their ability to focus on so many pieces of the stack at the same time. Because heaven knows, data scientists have a lot going on at the top of the stack. They've got to think about the implications of their models, all these statistical fallacies. There's a whole discipline to data science that doesn't involve these underneath layers of the stack. So that's what I think of as us coming in as MLOps professionals, is filling that gap so that we can enable data scientists to do higher quality work faster. And we want to do this through systems abstraction. Data scientists don't need low code, they need low systems. Because they can write code. They're developers, they can write code. That's not the problem. So what we want to do here with systems abstraction is to provide a good enough encapsulation layer so that they can keep their focus at the top of the stack where it belongs. Systems encapsulation is really hard, particularly in our ecosystem that's so young and so kind of evolving and maturing out from under us. So it's very, very common to have some systems encapsulation. It's like, okay, we've got this totally covered, but it's going to spring a leak for this particular thing. So, like, we're all good until you need to find the logs for that thing. And oh, you need to find the logs for that thing. Okay, let me install kubectl and teach you how to use it. And, y'all know that. So just to visualize this, the green is the top of the stack. That's where we're trying to keep our data scientists. Everything else is what we're trying to encapsulate, not because they're too dumb, but because they have too much else to focus on and we are trying to accelerate them. So this tends to invoke a design trade-off between being too opinionated or too configurable. Jules, again, was kind of talking on this in this last talk about Ray. If it's too opinionated, you can't get it to do what you need to do. If it's too configurable, you can't get it to do what you need to do for different reasons. As a concrete example, you could think about App Engine is very opinionated. App Engine is very easy to use. It's serverless. You just give it your code. It goes and runs that somewhere. It scales, whatever, and it doesn't have GPUs. So it's too opinionated and it's too limited for what we need it to do. On the other hand, too configurable, again, it's probably not the best design choice to just hand your data scientist a raw Kubernetes cluster and say, good luck, it can do what you need it to do if you can get it there. So we're trying to hit that sweet spot in the middle of how do we do enough systems encapsulation such that there's still room to do more configuration if needed. So to do this and enable this kind of high-tech stuff, we went super low-tech. So are y'all ready for the big reveal? To get GPU capability, we do repo templating. Isn't that exciting? So repo templating is not cool. It's not like, we're not going to have a conference about repo templating, but it works. It really, really works. We found this to be the right level of abstraction for our data scientists to give them a stable base from which they can go off and extend and do the work that they need to do. So for us at Mailchimp, some of the stuff that's included in our repo template, base containers to kind of encapsulate the systems level stuff, places to integrate your custom Python code, some starter like requirements files, basic run scripts for your application, some basic CI/CD stuff so that there is CI/CD because there may not be if we didn't provide that. And we get this GPU capability basically at the container layer in this template. So both at the Kubernetes layer, which I didn't really talk about, but in the pod configuration, when you're attaching that GPU, we provide that templating. And then we also provide a base container that is mostly GPU capable for whatever machine learning library you want to throw at it. So some challenges we've encountered with this are, is your base container general enough? And what we found is that one of the reasons I know that TensorFlow is a diva is that it's not general enough to support whatever version of TensorFlow. So that's been the challenge that we've encountered. There's also some design decisions you have to make when you consider the kind of common applications that a data scientist needs to produce. So a Python library versus a batch job versus an online service. Do you want to cram all of that into one repo template? Do you want to split it out? If you've got this template that's kind of like your source of truth for how we do this, and you get a bug fix to it, how do you update children of that template? Interesting and surprisingly kind of deep challenge there. And then we've kind of talked about the GPU capability piece of this. So little hard won wisdom. This is, I guess, our no BS data conference. We found that rather than trying to cram everything into one template type, it's better to have multiple templates. And if you as kind of the team that provides the stuff want to have your own like underlying layer of stuff that's all the same, cool. But what you present to the data scientist is more kind of split out about like, here's your library starter base. And it may have a lot of similar components, but it is different from your batch job interface and that kind of thing. We really have learned that we kind of cannot and should not limit our data scientists in their choice of library. It's really, really important for us to empower data scientists however they need to be empowered. And that does not include saying, oh, you can only use PyTorch because TensorFlow is a diva. It means figuring out how do we support TensorFlow because we're trusting our data scientists to make a reasonable choice and to be asking for this because they have a really darn good reason for it. We found that having one base container that's kind of the data science container really isn't good enough. It's really better to have a curated list of options from which you can pick, accompanied by some good documentation that covers this GPU stuff well enough for folks to make an informed decision. And then finally, when we're doing these templates, when we first got on the templating train, it was like, oh yeah, template everything. It's great. And then found that we were trying to generalize too hard and trying to generalize over some weird stuff. So design it for the 90% case and leave room for the 10%ers to go do weird stuff. But don't try to wrap their weird stuff into the template. It's too confusing. So that's basically what I've got for y'all today. On the tech side and on the human side, just some final thoughts. To hammer it home one more time, MLOps is a hyper-technical field that is all about people. We do all of this in service of empowering our data scientists to move fast and get great insights for our business and to do the work they need to do it faster and do it to a higher degree of quality. On a totally different level, when you're confused about GPU stuff and CUDA weirdness, strace and ltrace are your friends. Repo templating is also your friends. And just in general, don't be afraid to be uncool to do cool stuff. Repo templating, it's not cool. So that's what I got for y'all today. I'm happy to take questions now, and I did want to mention that on the schedule, my office hours are going to be after lunch, so just FYI, I will be there, but after lunch. So thank y'all.